All right. Welcome back, everybody, to another deep dive into the world of numbers, sequences, all that fun stuff.
Yeah.
Today, we're going to be looking at mosaic numbers.
Okay.
And, our source for this, as always, is going to be the OEIS, the Online Encyclopedia of Intersequences.
Right.
And this one is it's a pretty cool sequence. It's, I think it's entry A00000026.
Yeah, that's the one.
So we're going to jump into it and take a look and see what we can find out about mosaic numbers.
Sounds good.
Yeah, so the OEIS starts off giving us the definition of mosaic number. And it says if n product, PJKJ, then AN product, PJKJ.
Okay.
Now, you being a mathematician, you probably see prime factorization going on there, right?
Absolutely.
And that's going to be a big part of what we're talking about today.
Yeah, breaking down those numbers into their prime factors.
Yeah, exactly.
It's like for finding those building blocks of a number, and then we're going to kind of rearrange them in a specific way to create this mosaic number.
Okay, because they're pretty fascinating.
So is that what makes it a mosaic number then? That specific rearranging?
Yeah, you can think of it that way. So like if you take the number, let's say 24,
Gotcha.
You can break it down into its prime factors, which are 2, 2, 2, and 3.
Right.
So that's 2 cubed times 3.
Okay.
Then to get the mosaic number, you multiply each prime by its exponent. So 2 times 3, then times that 3 by its exponent, which is 1.
Oh, okay. I see.
And you end up with 6 times 3, which is 18.
Got it.
So 18 would be the mosaic number of 24.
That's pretty cool. So I was looking through the entry, and it mentions this thing about square-free numbers and their mosaic numbers.
Yeah, square-free numbers, remember, those are the numbers that aren't divisible by any perfect square other than 1.
Right.
So like 10 would be square-free because it's 2 times 5.
Right.
But like 12 wouldn't be because it's divisible by 4.
Which is 2 squared.
Exactly.
So the interesting thing about square-free numbers is that their mosaic number is actually just the number itself.
Oh, okay.
Like, take 10, its mosaic number is also 10.
That's interesting. So why is that?
Well, it's because all the exponents in the prime factorization of a square-free number are 1.
Okay.
So when you multiply each prime by its exponent, you're essentially just multiplying it by 1, which doesn't change anything.
Gotcha.
It's like a little identity trick
for
square-free numbers.
So then how does that play into the whole sequence of mosaic numbers?
Well, that's where things start to get a little bit more...
a little more interesting.
Interesting, yeah.
Yeah.
So, like, you look at the mosaic number sequence. It starts off 1, 2, 3, 4, 5, 6, 7, 6, 6, 10, and so on.
Hold on. I see it.
You see that repetition there?
Yeah, the 6 is repeating.
Exactly. And that's kind of a clue to how these mosaic numbers work. Like, if you look at the numbers 8 and 9, they both have different prime factorizations, right? But their mosaic numbers end up being the same, which is 6.
Huh. So that repetition isn't just random?
Not at all.
It's like a result of how those prime factors and exponents
they play together.
come together. Okay, that's pretty cool.
It is, isn't it?
So I was looking at the OEIS entry, and it also gives this formula. AN, A005361N, A007947N.
Oh, yeah.
And I was completely thrown for a loop.
Yeah.
Like, first of all, what does that even mean?
Well, you know how we said the OEIS is kind of like this giant web of interconnectedness?
Yeah, definitely.
Well, this is like a prime example. So you've got A005361, which lists the largest prime factor of each number.
Okay.
And then you've got A00007947, which gives you the sum of the exponents in the prime factorization.
So it's like looking at the same number in 2 totally different ways.
Exactly.
But then somehow the combination of those 2 things gives you the mosaic number.
Yeah, it's pretty wild, right?
Yeah, it's mind-blowing.
It really shows you how these seemingly different concepts in number theory are actually all connected.
I'm starting to see that, yeah.
And, we'll see later on how this idea of mosaic numbers being like a shadow or a projection.
Oh, right. You mentioned that before.
Yeah, a projection based on the prime factorization that'll become a bit clearer as we go along.
Okay, so then this entry also mentions something called an asymptotic formula.
Right.
Sum K1.
Right.
AKCN2. Can you help me understand that?
Yeah, so an asymptotic formula tells us about the long-term behavior of something.
Okay.
In this case, it's talking about the sum of the mosaic numbers.
Got it.
So basically, as n gets really large, like astronomically large, The sum of the first and a mosaic numbers starts behaving like a constant multiplied by n squared.
So the bigger the set of numbers, the more predictable their mosaic number sum becomes.
Exactly.
It's like they settle into some kind of pattern.
Yeah, you could think of it that way.
Okay, so I'm noticing that the OEIS entry mentions a paper by B. Gordon and M.M. Robertson titled Two Theorems on Mosaics.
Right.
What can you tell us about those theorems?
Well, those theorems, they provide some serious mathematical backing for what we've been talking about.
Yeah.
The first theorem, it delves into this connection between the divisors of a number and the divisors of its mosaic number.
Oh, okay.
It's like it shows how these seemingly separate aspects are actually intertwined.
Okay, I'm definitely intrigued. So tell me more about this connection between divisors.
Okay, well, it can get pretty technical, but the gist is this. If you know the divisors of a number, you can actually say something about the divisors of its mosaic number.
Interesting.
Like, there's a kind of mathematical inheritance happening there.
Huh. Okay.
Yeah, it's pretty fascinating.
So even though we started out talking about prime factorization and rearranging those prime factors,
Right.
there's this whole other thing going on with mosaic numbers and divisors.
Absolutely.
Okay, so what about the second theorem?
Yes. The second theorem deals with something called the average order of the mosaic number function.
Average order.
Yeah, now imagine this. You've got a room full of people, right?
Okay.
And you want to find their average height.
Right.
So you'd add up everyone's height and then divide by the number of people, right?
Makes sense.
Well, the second theorem is kind of similar, but instead of people and heights, we're dealing with numbers and their mosaic numbers.
Okay.
So it gives us a formula to calculate the average value of the mosaic numbers of the first and positive integers.
So it's like finding the average height of the mosaic numbers in a set of numbers.
Exactly. And what's really cool is that as n gets incredibly large, this average value approaches a specific constant.
So even though mosaic numbers themselves can be kind of unpredictable,
Right.
their average over a large set becomes predictable.
Yeah, it's another example of this underlying order that we find within mosaic numbers.
That's pretty amazing.
It is, isn't it?
Yeah, it's really cool. So, earlier we spent some time talking about the repetition of the number 6 in the mosaic number sequence, and it was really interesting. But as we get deeper into these theorems and the connections to divisors and average values, it almost feels like that repetition was just a little sideshow.
It's true. The repetition of 6 is more of a surface-level curiosity.
Okay.
It highlights the role of prime factorization, but those theorems by Gordon and Robertson really take us much deeper into the heart of the theory.
Right, and we also can't forget that formula connecting mosaic numbers to sequences A00005361 and A007947.
Absolutely.
That was mind-blowing.
Yeah, that's another great example of how different areas of number theory are all intertwined.
Yeah, it really is.
It's like, you pull on one thread and it unravels this whole tapestry of connections.
I'm starting to see that, yeah.
The OEIS is really more than just a catalog of sequences. It's a roadmap to this vast network of mathematical relationships.
Okay, well, on that note, let's take a quick break, and when we come back, we'll delve even deeper into those fascinating connections and the implications of those theorems.
Sounds good.
All right, we'll be right back. Welcome back, everybody. We're in the middle of our deep dive into mosaic numbers.
Yeah.
And, before the break, we were talking about how mosaic numbers are like a shadow of the original number. I'm kind of stuck on that.
Yeah.
I think I need you to kind of unpack that a bit more for me.
Okay, sure.
Like, what exactly do we mean by shadow in this context?
Well, think about it like this.
Okay.
You have like a 3D object, right? And you shine a light on it.
Okay.
The shadow that it casts is like a 2D representation of that object. It captures some of the features, but not all of them.
Gotcha. So how does that relate to mosaic numbers?
So think of the original number as the 3D object.
Okay.
And the mosaic number is like its shadow.
Okay.
It's a projection that's based on its prime factorization.
Okay, so we're taking like the essence of the number, its multiplicative structure, and transforming it.
Right, we're focusing on the prime factors and how they combine.
Okay, and that gives us the mosaic number.
Exactly.
Okay, that makes a little more sense now.
Yeah.
So, before the break, we were also talking about the two theorems.
Oh, yeah, by Gordon and Robertson.
Yeah, those ones. And the first one talked about the connection between divisors.
Right.
Can you give me a specific example of how that works?
Sure. Let's take the number 12, for example.
Okay.
The divisors of 12 are 1, 2, 3, 4, 6, and 12.
Right.
And the mosaic number of 12 is 6.
Okay.
Now, the divisors of 6 are 1, 2, 3, and 6.
Wait a minute, I see it.
Yeah.
The divisors of 6, which is the Mosaic number, are like a subset of the divisors of 12.
Exactly, you got it.
So the original number.
It's a pretty neat connection.
Yeah, it is.
It's not just a coincidence either.
Okay.
That theorem proves that this relationship holds true
Oh, wow.
for any number, and it's Mosaic number.
Okay, that's really elegant.
It is, isn't it?
It's like this hidden harmony or
So
something.
I like that, yeah.
So, okay, the first theorem connects them through their divisors. What about the second theorem?
Ah, the second one.
The one about average order.
Yeah, average order.
I'm not even sure what that means.
Okay, well, think of it this way.
Okay.
Let's say you have a room full of people.
Okay.
And you want to find their average height, right?
Right.
You'd add up everybody's height and divide by the number of people.
Yeah, pretty simple.
Now, the second theorem is similar, but instead of people and heights, we're dealing with numbers and their Mosaic numbers.
Oh, I see.
So the theorem gives us a formula to calculate the average value of the Mosaic numbers for, like, the first and positive integers.
Got it.
It's kind of like finding the average height of the Mosaic numbers in that set of numbers.
Okay, so what does that tell us?
Well, the interesting thing is that this average epsilon gets super large.
Yeah.
It approaches a specific constant value.
So even though the individual Mosaic numbers can be kind of all over the place?
Right, they jump around.
Yeah.
But the average over a large set becomes very predictable.
That's pretty wild.
It is.
So we've got this connection through divisors.
Yeah.
We've got this predictable average. What else is there?
Well, we talked about that repetition of the number 6.
Yeah, at the beginning.
Right, and while that's interesting, it's more of a surface level thing.
Okay.
The theorems really take us deeper.
Oh, okay.
Into the theory of Mosaic numbers.
And then there's that formula connecting the Mosaic numbers to those other sequences.
Oh, yeah. AD005361 and AD007947.
Yeah, that one blew my mind.
I know, right?
It's like all these different parts of number theory are connected somehow.
Exactly. That's what makes it so fascinating.
Yeah, I'm starting to see that.
It's like a giant puzzle where all the pieces fit together.
The OEIS is really amazing.
It is. It really is.
Okay, well, I think that's a good place to stop for now.
All right.
But we're not done yet. We've still got more to explore with Mosaic numbers, so stay tuned.
We'll be right back.
All right, welcome back to the show, everyone. We're wrapping up our deep dive into Mosaic numbers.
That's right.
And, I've learned a lot.
Good.
Like, I didn't realize how much there was to these numbers.
Yeah, they're pretty fascinating, aren't they?
Yeah, definitely.
So, there was one more point in the OEIS entry that I wanted to circle back to.
All right.
It mentions that Mosaic numbers are sometimes called the multiplicative projection of n.
Right.
And we talked about that before with the shadow analogy.
Yeah, with the shadow analogy.
Right, but I think it's worth revisiting.
Yeah.
Because that term multiplicative projection, it always makes me think about maps.
Oh, maps.
Yeah.
Interesting.
You know how maps represent a 3D world on a 2D surface?
Right.
Well, in a way, that's what we're doing with Mosaic numbers.
Okay.
We're taking a number with all its layers and we're creating a map of its multiplicative structure.
So, like, we're focusing on its prime factors and their exponents.
Exactly.
Okay, I see that.
And just like a map can guide us through unfamiliar territory, Mosaic numbers can help us understand the world of numbers.
They can reveal those hidden patterns.
Precisely.
Okay, well, this whole deep dive has been a real eye-opener for me.
I'm glad to hear that.
And I have to say, you've been an amazing guide.
Well, thank you.
I feel like I have a much better grasp on these numbers now.
Good.
So, to everyone listening out there,
yeah,
keep exploring the world of numbers.
Absolutely.
Dive into the OEIS, pick a sequence that intrigues you, and see where it leads.
There's so much to discover.
You never know what you might find.
That's right.
Until next time, keep those minds curious and keep diving deep.
See you later, huh?